So we saw in example 3a, there are different ways of solving a problem like this, and it really depends on the information that you're given. With A and B, the most efficient method is just to use the reciprocal and quotient identities. So for part B, we would say we have sine, it's 3 over 5, so cosecant is a reciprocal of that, 5 over 3. We have cosine, it's negative 4 over 5, and secant is a reciprocal of that, so negative 5 over 4. And then we know that tangent is sine theta over cosine theta. So we have 3/5 over negative 4/5. So we have the numerator 3/5 times the reciprocal of the denominator, 5 over negative 4. The 5's cancel out, and we get negative 3/4. And then the reciprocal of that is cotangent, so negative 4 over 3. All right, so moving on to example 4, applying the identity sine squared theta plus cosine squared theta equals 1. We saw where this identity comes from last week. It comes from the equation of the unit circle. So here's the equation of a circle centered at 0, 0 with a radius of 1. And we know now that x is the same as cosine theta and y is the same as sine theta. So substituting cosine and sine in for x and y, respectively, we would get the identity sine squared plus cosine squared equals 1. So let's use that identity for example 4. And again, example 4 is another one of those ones where you have different options as far as how you can solve it. And I just want to show you a new way, and that's using this identity. If sine theta equals negative 3/5 and cosine theta is less than 0, find the values of the other 5 trig functions. So we have sine, and all we know about cosine is that it's negative, it's less than 0. So let's fill in sine theta as negative 3/5. So what else do we know if we know sine? We know it's reciprocal. Cosecant is negative 5 over 3. So that's 1 down, 4 more to go. So we're going to use this identity, sine squared theta plus cosine squared theta equals 1 to solve this problem. But you could also draw a picture like we did in example 3. You have 2 of the 3 sides. So what you would need to do is figure out which quadrant theta is in. Make sure to label the sides properly, and then find the missing side. Once you have all 3 sides, you can find the other 4 ratios. So let's use this identity. Sine is negative 3/5. So substitute that in. We have negative 3/5 squared plus cosine squared equals 1. Negative 3/5 squared is 9 over 25. Bring everything else down. And I'm going to rewrite 1 as 25 over 25 so that I have a common denominator, because I see that I'm going to have to bring over that 9/25. So subtract 9 over 25 from both sides. And I get cosine squared theta equals, let's see, 25 minus 9 is 16. So 16 over 25. What do we do next? We need to solve for cosine theta. So let's take the square root of both sides. And we get cosine theta equals, remember when you take the square root of something squared, add the plus or minus. Plus or minus square root of 16 is 4. Square root of 25 is 5. So we have cosine theta is either positive 4/5 or negative 4/5. So we have to choose one of them. It can't be both. So let's go back to the problem, reread it. It tells us that cosine theta is less than 0. So cosine theta is supposed to be negative, not positive. So that tells us that cosine theta is negative 4/5. Negative 4/5. So we can now find secant. It's negative 5 over 4. Tangent is sine over cosine. So we have negative 3/5 over negative 4/5, which is negative 3/5 times 5 over negative 4. The 5's cancel out and the negatives cancel out. So we get that tangent is positive 3/4, which means that cotangent is positive 4 over 3. Okay, next example, example 5. Let s equal negative 3 pi. If possible, find the 6 trig functions of s. So negative 3 pi, last week we learned what quadrantal angles are. They're angles that fall on either the x or y axis. And they look like multiples of pi, like negative 3 pi, or multiples of pi over 2. So those are the quadrantal angles. So that means that we're looking at one of these 4 terminal points. Using the unit circle, the coordinates of these points are 1, 0, 0, 1, negative 1, 0, and 0, negative 1. So what we need to do is sketch the angle. Where exactly is negative 3 pi? So negative 3 pi is negative 2 pi plus another negative pi, or negative 1 pi. So that means I need to do a full rotation clockwise plus another half rotation. So starting in standard position, we rotate a full 2 pi, a full rotation. That's 2 pi, and then another pi brings us to negative 3 pi here. So that tells us that this is our terminal side, the negative x-axis here, and that's our terminal point, negative 1, 0. So this is where negative 3 pi is. So let me erase the other points. All right, we know with the unit circle that the x-coordinate gives us cosine and the y-coordinate gives us sine. So that means sine of negative 3 pi is 0. Cosine of negative 3 pi is negative 1. From here we can find the other 4. The reciprocal of sine cosecant is going to be some number over 0. So let's just say it's 1 over 0. So the problem with the reciprocal of 0 is, how do we write 0? How do we rewrite 0? So there are lots of ways we could rewrite 0. We could write it as 0 over 1, 0 over 2, 0 over negative 1. So any number that we put in the denominator, if 0 is in the numerator, it simplifies to 0. So when we talk about the reciprocal of 0, we don't know which one to choose. How do we choose? Is it 1 over 0, 2 over 0, negative 1 over 0? We don't know. So pick whichever number you prefer. It doesn't matter which number you pick because any number over 0 is always going to be undefined. So that means that cosecant is undefined at negative 3 pi. Okay, so now we can find secant. The reciprocal of cosine is negative 1. Tangent is, again, sine over cosine. So sine of negative 3 pi over cosine of negative 3 pi, which is 0 over negative 1, which is 0. So we come to the same issue with cotangent. The reciprocal of 0 is undefined. So for tangent, cosecant, secant, and cotangent, we have the possibility of having x values where the function is undefined. So let's review what that means about the graphs of these functions. So whenever we want to show that a function is undefined at a specific value, there are different ways that we can show that in a graph. We learned that we can show that with a vertical asymptote, and we learned with rational functions that we could show that with a hole. So with a situation like this, x cannot be negative 3 pi for cosecant, for example. So we want to show that x can never be negative 3 pi for any y value, so we show that with an asymptote, and specifically a vertical asymptote. So let's look more at different values of all 6 trig functions, and let's look at where the functions are undefined. We have, for tangent, for example, tangent is undefined at pi over 2 and at 3 pi over 2. Cosecant is undefined at 0 and at pi and 2 pi. Secant is undefined at pi over 2 and 3 pi over 2. And then cotangent is undefined at 0, pi, and 2 pi. So it looks like tangent and secant have the same domains, and cosecant and cotangent have the same domains. They're undefined in the same places. So let's take a look at the graphs. We'll start with the tangent function. So this is what the tangent function looks like. Y equals tangent of t. So one period of tangent is this piece right here. This is one period. Not specifically that piece, but that's what one period looks like. So we copy this piece and we paste it to the left and right, and we get our tangent function. Also notice the vertical asymptotes. So we have a vertical asymptote at pi over 2. We have another one at 3 pi over 2, negative pi over 2, negative 3 pi over 2. So the period of tangent is pi, as opposed to 2 pi for sine and cosine. We said that for sine and cosine, we call them periodic functions. They're cyclical or circular functions that repeat every 2 pi. The values repeat every 2 pi. For tangent, however, the values repeat every 1 pi. So that's why the period is pi. So let's take a look more into the vertical asymptotes and talk more about the domain of the tangent function. So we can see where the vertical asymptotes are. So the vertical asymptotes are at negative 3 pi over 2, negative pi over 2, positive pi over 2, and positive 3 pi over 2. Just based on this graph that we're given. But we have an infinite number of vertical asymptotes. So there's more going to the left, there's more going to the right of 3 pi over 2. But when we want to talk about the domain of this function, we don't want to have to list out every single vertical asymptote because there's an infinite number. So we want to be as concise as possible. So let's use set notation for the domain of tangent. It's the set of all x such that, remember when we have vertical asymptotes, we, in set notation, say where the function is undefined or what x cannot be. So the function is undefined, or x cannot be this. So we have a long list here. So when we have a domain like this, a restricted domain, we always write it in terms of the vertical asymptotes, if there are any, and we start with the smallest possible x value. which is pi over 2 for the vertical asymptotes. So that's the smallest positive x value where there's a vertical asymptote. And then we want to talk about how all of the other vertical asymptotes are related to pi over 2, to x equals pi over 2. So let's compare pi over 2 and then the next asymptote to the right. So the difference between these two asymptotes is pi. The difference between these two x values is pi. As we can see here, the period is pi. And then the difference between pi over 2 and the vertical asymptote to the left, negative pi over 2, is also pi. And then we just keep adding or subtracting pi in between every two vertical asymptotes. So that's the relationship between the vertical asymptote at x equals pi over 2 and all of the other asymptotes, is there's a difference of a multiple of pi. So we say that the domain is the set of all x such that x is not equal to pi over 2 plus pi n, pi times n, where n is any integer. So for example, if n was 1, if n is equal to 1, that'll tell us where we have another vertical asymptote. So pi over 2 plus pi times 1 is just pi. And then finding a common denominator, we have pi over 2 plus 2 pi over 2, which is 3 pi over 2. So that gives us this vertical asymptote here. If n was, let's say, negative 2, we have a vertical asymptote at pi over 2 plus pi times negative 2. So we have pi over 2 minus 2 pi, which again we need a common denominator. So we have pi over 2 minus 4 pi over 2, which gives us negative 3 pi over 2. So that's this vertical asymptote here. So that's how we interpret a domain like this. And we'll look next time at the domains of cosecant, secant, and then cotangent. We're going to write the domains similarly.